Okay, we stop at distinguish between EMF and PD, right? Always remember, EMF is from the cell. Normally, the examiner won't tell you there's an internal resistance there. They will want to test you whether you understand or not. And then there's the potential difference. Okay. Okay. How do we find the EMF and internal resistance of a cell? This is your page 100, number 7. Right? There's your cell. There's the internal resistance. There's the emitter, ideal voltmeter. There's your variable resistor. You want to plot the VI graph. Okay. You want to determine the EMF and internal resistance of a cell. Page 100.
Can you repeat everything again, sir? Because my Zoom was crashing just now.
We end the last topic.
Okay.
Distinguish between EMF and PD. EMF is just that one. Usually that's called EMF or E is provided by the source. And then examiner won't tell you there's an internal resistance there. You have to know there's an internal resistance there or there. Put that by yourself. And then this is the external load. The PD is always across the external load. Right? So it means that if you have external load, the PD is no more 9 volt anymore. Right? You put a voltmeter to read it. That one you calculate later on. Okay. Determine the EMF internal resistance of a cell. Page 100 in the book, number 7. There's your dry cell. Internal resistance R, EMF E, ideal emitter, ideal voltmeter. There's a variable resistor. You want to plot V against I graph. So you should be able to write the equation, right? R, vary R, change this R, and each time read this V and this I, this A or I. Then tabulate it, then plot a graph of V against I. Right? And then you will get the equation of graph. Remember that equation there? There's your E is your source. And then there's your V. V is across the big R. V. And I times R. And this one, there's a potential difference across here. So rewrite that. Right? We want V over I. So we take the I out to the other side. It becomes negative. Right? Just rewrite it because our I is a variable. So compare to the equation of a straight line. This is the equation of a straight line. Compare with that. Right? We got a straight line graph with negative gradient. And then the C, that y-intercept is your E. Gradient, right? That gradient there is your minus R. Right? E is here, y-intercept. So you should be able to find from the graph your EMF and R. Okay?
Okay.
R of the external resistor increases, right? As R increases, the terminal potential difference V increases. Remember, this is I times R. So as our R increases, this one must increase. Okay, the current will go down. Right? Current in circuit decreases. As you increase this one, less and less current will flow through the circuit. Okay, power output and efficiency. Power output increases, right? As your, right? This is your internal resistance. We are changing R. So our power output start from 0 and increases to a maximum when the external resistance equals the internal resistance. Right? Power is maximum. When your power, then after that the power decreases again as your R is greater than R, small r. and becomes 0 where R is very large. Efficiency is slightly different, right? Efficiency increases as the external resistance R increases. At R, right, where your big R equals to small r, internal resistance, then it's 50% here. So where the external load is very much greater than internal resistance, then the efficiency is 100. So you want efficiency 100, you use as large an external load as possible. You want power output largest, then you choose the external load equals to internal resistance. That's what this all means. Output power and efficiency, right? Rate of energy supplied by the cell, right? That is the energy by the source dissipated here and here, right? In the external resistance, internal resistance. We got your P out, P wasted, P supply. So P out is just your I squared times R. Wasted is same, I squared times the small r. Power output is this one, right? Or this is the one that is useful to us. This one is lost, no use to us, we cannot use it. Right? That's why this is called power output or useful power. It's I squared R. Wasted or lost as heat is I squared R. So efficiency is just the power output over your power supply. P out, PS, P out is this one, I squared R. PS is this one, supply is this one, I square and carry on, you get that value. Cancel the I square, get R over R plus R. Okay, so that's how we get our graph previously. So if our R is very much greater than this small r there, we can neglect this small r. R and R cancel is 1 or 100%. Okay.
Why the out is R and then in is R plus R?
What do you mean? We are just deriving the equation, that's all. That's our equation that we derive.
Oh, this one just memorize me lah, nothing to understand.
This is the capital R is the one that we change. Small r is the one inside here. There's a fixed for each particular power supply. Is power source is 6. So we are just changing the capital R as well. And this one is just to show you that efficiency increases with load. That's all. That's how we get a curve. Right? Curve is follow this equation. Right? Where our external load, this one, is very small, much smaller than that. Right? Where right? You look at this equation there. This one is larger than this one. This is very small. Then we can neglect this one. That's why we get this equation. Okay, so we can see that this part is more like a straight line. This part near here. Then at this part there, where that R there is very much greater than that, then it'll be 100%. Right? But the current is very small, as we say. If R is very large, the current in the circuit is very small. Variation of power output with load. Okay, your power output, we cannot use I square and R together because as your R changes, your current changes. So we have to replace this I before we can get anything useful. Right? So that's why we use this equation, E equals to I times R plus R. That's your Kirchhoff's voltage law. Right? Then we can find our I, take our R plus R to the other side. We got that equation. Then replace this I with this one. Right? You get your square that E square, R plus R square, and this is big R is over there. Right? You can roughly see what is going to happen where our very small value R here, very small value is very small. Then we get R square. We can neglect this R square.
Yeah,
So
because cut off already. Eh? Oh.
yeah, this is just a math question. This big R is very small compared to this R. Then we can neglect
Oh.
this R.
Oh, okay. Okay.
And this is about here, around here. Right? So we can see it's a straight line graph. That part is a straight line. Right? Very small R value. Then at this part there, where our
So
R is,
then the calculation, the small r is neglectable lah.
when the big R is very much greater than the small R, right? Same thing. This one, where our big R is very much greater than R, small R, we can drop the small R. Right? There's the R square. We cancel the one R from here, one R from here, get 1 over R. So this one is like a hyperbola, this part. And then it's maximum where R equals to R. Right? Where the external load equals to internal resistance. And for our load greater than R, the power output decreases. We can derive, right? That is the derivation. Okay, that's the equation that we have got previously. So we can replace this one with our U, that one with our V. Okay, then dP naught dr. Okay, so we start with V, that's your V. Then we differentiate this one. Okay, so we get E square. Then after that, you got a minus there, U, that's your U. Differentiate your V, this one. Right, we get our 2, then we get R plus R. There,
Yeah.
then V square, that this one, the power 4. And cancel our R plus R, and R plus R here, and R plus R here. Okay, that becomes 3. We got our E square, take our E square out. So we still got R plus R here. This one become 1 already. This one become 1 already. And then this one becomes minus 2R left. And bottom becomes R plus R to the power 3. Okay, simplify some more. That's minus 2R. That's your R, so you still got minus R. Okay, so we can differentiate that, which we have done. We get our equation there. dP dr equals to 0. Then we get R equals to R. That's how we get that. So where R is infinite, no current flow, so no power transfer. So usually we want to use maximum power lah, because if we have power is very small, then we have to, like a loudspeaker, we have to amplify it. No point, right? Even though the efficiency is very low. Okay, try this question. Then we will finish it off for today. This is your SPM mode.
Okay. Current.
Yep, what's the current drawn from the cell?
Wait, that's it. 0.6.
Write down all the value there.
3/5.
Right? E equals to I R plus R. E is 3 volt. I then 20 plus 5.
Yeah, 3/25. Yeah.
Then the terminal potential difference.
Oh, wait. So terminal potential different. 0.12 times 20.
Yeah. Power supply.
Zero point 0.12 times 3, so it's 0.36.
Okay. E times I. So you got 0.36 watt. Okay. Not this one. This one. That's your E times your current.
The EMF.
That's the EMF. Right? We have calculated rate of energy wasted. We have to calculate all that. I send you as exercise. You can download it yourself so that you can do it on the paper itself.
Che, go back again, Che.
Okay. What do you want to see?
No, go back again, Che. I think I kind of missed the ABC.
You say you know how to calculate already. What's there to go back again?
Yeah, I know, Che. Just 1 minute. Okay.
Right? Wasted is I squared times the small r.
So,
That's all.
wait, the times 5, where did you get from?
5 ohm.
Where? Don't have also?
God lah, you never pay it. That's why you never download the question paper. I told you the question paper is there. 5 ohm here.
Oh, yeah, I did download it already.
Then you should be able to see from the question itself.
Okay.
Right? You can download either 4 in one page or 6 to one page if you want to, depend on your choice. You know how to do that, isn't it?
Yeah.
Then your power output, you should be able to calculate. Right? Supply minus your wasted.
0.288.
Right? So efficiency power output over power supply times 100. 80%.
Yeah.
Okay, so we have more or less got all this formula that you need to remember. And let me just, this one you can try yourself. I will send you the answer. Let me just try one question, then we'll finish for today. This one. Try the other question. We ask you next period, Saturday. A battery is marked 9 volt. What does this mean? Yeah, what is the answer?
Wait, answer. A.
Okay. B is your potential difference. Correct? Okay, answer is A. Okay, we'll finish for today. You can try the question under your check. The question I've sent you to you, the exercise, there are still others, objective one. And then you can also try the checkpoint. Checkpoint.
Yeah, can check.
My one. So we'll end today. Okay, you can go.
Okay, thank you, Che.
Bye-bye.
Bye-bye.
See you on
But Che.
Yeah.
Che.
See you on Saturday. Anything else?